All right, let's jump into another deep dive. At this time, we're looking at systems analysis and design.
Oh, yeah.
Which is, kind of a foundational text for software engineers. But, I think anyone can get a lot out of this.
Definitely.
Even if you've never,
never coded.
written a line of code in your life.
For sure.
We're going to try to give you that ha-ha moment about how software goes from just like
a light bulb.
A light bulb idea in someone's head to an app that you use every day or a website or whatever it is.
Exactly. Yeah, it's a really fascinating journey. And a lot of it isn't about writing code at all. It's about understanding people, problems, and processes.
And that's where our expert comes in today. Who has, years of experience in the field actually building software.
That's right.
So they can walk us through,
for sure,
how this stuff actually plays out in the real world.
Absolutely.
So I'm already hooked by this.
Okay.
Software development lifecycle idea.
Yeah, it's kind of a
grand
sweeping title.
So what is that in a nutshell?
So imagine it kind of like an architect's blueprint, but for software.
Okay.
The book calls it the SDLC, and it basically lays out these phases you go through.
Okay.
To build any piece of software, I can make sure that it's robust, user-friendly, and it actually solves the problem it's meant to.
So is it like a step-by-step recipe?
You could kind of say that.
Okay.
So it basically outlines 5 main phases: systems planning, systems analysis, systems design, systems implementation, and systems support and security.
Okay, so those are the 5 phases.
And they really build on each other.
Okay.
So just like you wouldn't start building a house by slapping on some bricks without a plan. You don't want to just jump into coding without first understanding what you're building and why.
Yeah, it's all about laying a strong foundation.
Exactly.
Okay, so walk me through those phases a little bit.
Sure.
What happens in that first stage, systems planning?
So systems planning is like deciding what kind of house you want to build and where you want to build it.
Okay.
You're defining the scope of the project. You're figuring out what resources you'll need,
Okay.
People, money, time, technology, and also you're getting buy-in from stakeholders.
So it's like a brainstorming and strategizing phase.
Exactly. You're setting the project up for success right from the beginning.
Love it.
Yeah.
What happens next?
So then comes systems analysis, which is all about understanding the problem you're trying to solve.
Okay.
This is where you really dive deep into the what and the who of the software. Who will be using it? What do they need it to do?
Right.
And the book emphasizes the importance of gathering requirements from users, from stakeholders, to make sure that the software meets their needs.
Right, because there's nothing worse than spending months building something that nobody wants.
Yeah, nobody needs it.
Or need. So how do you actually go about gathering those requirements?
So
that sounds like a challenge.
It can be.
Yeah.
So the book talks about techniques like interviews, surveys, and even observing people using existing systems.
Oh, interesting.
To see where the pain points are.
Okay.
The goal is to understand not just what people say they need, but what they actually do, how they interact with the system.
Oh, that's smart.
And all of this gets documented in a really detailed system requirements document.
Okay.
Which becomes kind of the guiding light for the next stage.
I like that.
Yeah.
A treasure map.
A treasure map.
Leading to software gold.
There you go.
Okay, so we've planned the project, gathered the requirements.
We got it all.
What happens in the systems design phase?
All right, so systems design...
Is this where the coding starts?
Not quite yet.
Okay.
So systems design is where you take all those requirements.
Okay.
And you start shaping them into a blueprint for the software.
Okay.
This is where you make decisions about the overall architecture of the systems, how the data will be structured, what the user interface will look like.
So you're essentially creating a model of the software.
Exactly.
But not actually writing the code yet.
Yeah, it's like sketching out the layout of your house.
Okay.
Deciding where the walls will go, how many rooms you'll have.
Gotcha.
Where the plumbing and electrical systems will run.
So, and just like with a house, you have different architectural styles to choose from.
Exactly. So the book talks about things like client-server architectures, where you have a central server handling the heavy lifting, and then clients like your computer or your phone accessing the server to use the software.
And that's how, like, most websites work, right?
You got it.
Okay.
The internet relies heavily on client-server models.
Okay.
And then within that, you have different approaches, like 2-tier and 3-tier architectures, which basically determine how the workload is distributed and how many layers are involved in processing requests.
This is getting a little technical.
We're getting there.
But I'm starting to see how all these pieces fit together.
It all comes together.
So we've designed the blueprint.
Mm-hmm.
What happens next in the software development lifecycle?
Oh, right.
Do we finally start building?
Yeah, we build. Yeah, the systems implementation phase. This is where the blueprint comes to life. It's like the construction crew showing up and actually building the house based on those architects' plans.
Gotcha.
So this is where the coding, the testing, and the integration all happens.
Ah, so this is where those mythical software engineers with their energy drinks and multiple monitors come in?
Exactly, yeah.
What exactly does coding involve?
So coding is essentially like translating those design specifications into a language that computers can understand.
Okay.
It's writing instructions, step by step, to tell the computer what to do, how to process data, how to respond to user input, and so much more.
So it's like writing a recipe for a computer to follow.
Yeah.
But I imagine it's a lot more complex than baking a cake.
A little more complex, yeah.
What about testing?
Okay, so testing...
Is that just about making sure the code doesn't have any typos?
Testing is way more than just checking for typos.
Okay.
It's about ensuring that the software behaves as intended, that it meets all those requirements that we gather, and that it's robust enough to handle all different kinds of scenarios.
So you're not just making sure the code works. You're also making sure that it works well.
Exactly.
And it does what it's supposed to do.
It does what it's supposed to do.
What happens if you find bugs or issues during testing?
So that's where debugging comes in.
Okay.
It's like being a detective, you know?
Okay.
You're tracking down the source of the problem, and then you're fixing it.
Gotcha.
And the book emphasizes that testing shouldn't be an afterthought.
Okay.
It should be integrated throughout the entire development process.
So you're checking your work as you go along.
Yeah, catch those errors early on.
Right.
Before they become bigger headaches down the line.
That makes sense.
Yeah.
Okay, so we've coded, we've tested.
Debugged
the software.
Debugged it all.
What happens in that final stage? System support and security.
So this phase is all about ensuring that the software runs smoothly and securely once it's released into the wild.
So it's like the after-sales service.
Exactly. Think of it like that.
You don't just build it and forget about it.
Nope.
You need to make sure it continues to work.
You got to nurture it.
Okay, so what kinds of things happen during that phase?
So it involves things like providing ongoing support to users. Fixing any bugs that pop up.
Yeah, because there's always going to be bugs.
Always bugs. Implementing security measures to protect the software from attacks.
Oh, right. Super important.
Very important these days.
Yeah.
And even making updates and enhancements to keep the software relevant.
Right, because software is constantly evolving.
It's always changing.
Okay, so we've gone through the entire software development lifecycle.
We did it.
It's quite a journey.
It's a journey.
But before we wrap up,
I
have to ask, how has the internet revolutionized all of this?
Oh, the internet. The internet has fundamentally transformed software engineering in countless ways.
Give me some examples.
It's changed how we design software, how we build it, how we deliver it, even how we use it.
Okay, I'm all ears. Tell me more about these changes.
All right, so the book mentions something called Web 2.0.
Okay, yeah, I wasn't really sure what that meant.
Yeah, so think of Web 2.0 as the shift from those static websites to those dynamic, interactive platforms that we use today.
Gotcha.
It's about user-generated content, social media, you know, the ability to collaborate and share information online.
So it's like the internet went from being a one-way street to a bustling town square.
Exactly.
Where everyone can participate.
Everyone's involved.
So how did that impact software development?
So for starters, it changed the way we think about the user interfaces. Software had to become more intuitive, visually appealing, and engaging to keep users coming back.
Because our attention spans are so short.
Exactly, yeah.
But it also led to some incredible innovations.
Oh, for sure.
Like, what about this software as a service concept?
Okay, so software as a service, or SaaS, as it's often called.
SaaS,
is a way of delivering software over the internet on demand. So instead of buying software and installing it on your computer, you access it through a web browser.
So I don't have to worry about installing updates or managing servers.
Exactly. It's all handled by the SaaS provider.
It's like renting an apartment versus owning a house.
Perfect analogy.
That's a good one.
And that convenience has made software incredibly popular, especially for businesses. Think about email services like Gmail or cloud storage like Dropbox. Those are prime examples of SaaS.
You're right. I use those every day and I never even think about it.
There you go.
So the internet made software more accessible, more interactive.
More accessible.
And even changed how we pay for it?
Exactly.
What a game changer.
Huge game changer.
What other impact did the internet have on software engineering?
So it's also led to a rise in outsourcing, where companies can leverage global talent pools and potentially reduce costs by hiring developers from anywhere in the world.
Right.
And speaking of developers,
Yeah.
the role of a software engineer has become even more complex
Okay.
and demanding in this internet-driven world.
In what ways?
So, in addition to those strong technical skills,
Mm-hmm.
you need excellent communication and collaboration abilities.
Okay.
You also need to be adaptable and a lifelong learner.
Right.
Because technology is always changing so rapidly.
Like being a jack of all trades in the tech world.
Yeah, pretty much.
Okay.
You got to constantly be learning and growing to stay ahead of the curve.
So we've talked about the SDLC, the impact of the internet.
Mm-hmm.
What about e-commerce?
E-commerce.
That's a huge part of the internet landscape.
Yeah.
How does software engineering play into that?
So e-commerce is a really fascinating example of how those software engineering principles are applied to real-world business challenges.
Okay, tell me more.
It's not just about building a website with a shopping cart.
Right.
It's about designing a secure and reliable system that can handle transactions, manage inventory, process payments, and provide a seamless experience for customers.
So break it down for me a little bit.
Sure.
What are some of the key things that software engineers have to think about when they're building e-commerce systems?
So e-commerce architecture often involves multiple tiers.
Okay.
It integrates various technologies like web servers, databases, payment gateways, security protocols.
So it's complicated.
It can get pretty complex, yeah.
What are some of the different approaches to building these systems?
So you have different approaches ranging from in-house development, where you build everything from scratch, to packaged solutions, which are kind of pre-built systems that you can customize to some extent, to service providers who basically handle everything for you, from hosting to payment processing.
So it's like choosing between baking a cake from scratch.
Yeah.
Using a cake mix.
There you go.
Or just ordering a cake from a bakery.
Exactly.
It all depends on what you need.
Needs and resources.
Okay. And then within those e-commerce systems,
you
have different processing methods to consider.
Right. So you have things like online processing, which handles transactions immediately in real time.
Right.
And then you have batch processing, which collects those transactions and processes them in groups at a later time.
So online processing is like ordering a coffee and getting it right away.
Yes.
And batch processing is like
pre-ordering your groceries and picking them up later.
I liked it.
Each method has its pros and cons depending on the specific application.
Makes sense.
Yeah.
Wow, we've covered a lot of ground here.
We've covered some ground.
Web 2.0, softs, e-commerce architectures.
It's a lot.
Different processing methods.
Yeah.
I'm starting to feel like a seasoned software engineer myself.
You're getting there.
But remember, this is just the tip of the iceberg.
Just the tip.
There's so much more to explore.
So much more.
In the world of software engineering.
Endless possibilities.
Speaking of which, before we wrap up, we should touch on networks.
Networks, yes.
Because after all, without networks, there wouldn't be an internet.
The internet wouldn't exist.
Let's dive into that.
Okay.
What are networks and how do they work?
You're absolutely right. Networks are like the nervous system of our digital world. They're a web of interconnected devices that can share information, your phone, your laptop, even your smart refrigerator. They're all part of networks. And the internet itself is a massive network of networks.
Okay, so it's all about connections, but the book mentions something called network topologies. What does that even mean?
Good question. Topology refers to the arrangement of devices in a network. It's like a blueprint that determines how data travels between different points. Imagine different ways to connect cities with roads. You could have highways, back roads, roundabouts, and so on. Each arrangement would impact traffic flow and efficiency.
So network topologies are like different roadmaps for data.
Exactly. And just like with road systems, some topologies are better suited for certain situations than others. The book talks about a few common ones, starting with the hierarchical model. This one is kind of like a traditional corporate hierarchy with a powerful central device at the top controlling everything below it.
So it's like a pyramid structure with the boss at the top and everyone else reporting up the chain.
That's the idea. This model was popular in the early days of computing with mainframe computers, but it has a major drawback. If that top-level device fails, the whole network can go down.
Yikes, that's a single point of failure, not very resilient. What are some other options?
Well, there's the bus topology, which is like a single highway connecting all the devices. It's simple and cost-effective, but it can get congested if too many devices are trying to transmit data at the same time.
So it's great for a small town, but not so great for a bustling metropolis. What about ring networks? I'm picturing devices arranged in a circle.
You got it. In a ring topology, data travels in one direction around the circle, and each device acts as a repeater, boosting the signal along the way. It's like a relay race where each runner passes the baton to the next.
But what happens if one device of a ring fails? Does the whole thing break down?
Some ring networks have mechanisms to bypass a failed device, but they're not as common as other topologies. Now, the most popular type you'll encounter is the star network here. All devices are connected to a central hub, kind of like a bicycle wheel, with the hub at the center and the spokes radiating outwards.
So if the hub fails, everything goes down.
That's the downside, but hubs are typically quite reliable, and star networks are easy to manage and expand, which makes them a popular choice. Then you have mesh networks, which are like super connected star networks with multiple paths between devices. This makes them very resilient because if one connection goes down, data can simply take a detour.
That sounds impressive, but probably also complex to set up.
You're right, mesh networks are more complex and expensive, but they offer high reliability, which is crucial for critical systems. So the choice of topology really depends on factors like the size of the network, the level of reliability needed, and of course, budget.
It's like choosing the right transportation system for a city. You wouldn't build a subway system for a small village, right?
Exactly. Now, speaking of connections, we can't forget about wireless networks. Wi-Fi has become so essential in our lives, and it's a great example of how network technology continues to evolve.
Right. I can't imagine life without Wi-Fi. But how do wireless networks actually work?
Instead of physical cables, they use radio waves to transmit data, which is why you can connect to the internet from your couch without being tethered to a wall. And just like wired network, they use those same topologies we discussed. You can have wireless star networks, mesh networks, and so on.
So the way devices are arranged logically is the same, whether it's wired or wireless. That makes sense.
Exactly. Now, you might have seen labels on routers like 802.11ac. Those refer to the wireless network standards, which are like rules that ensure different devices can communicate with each other. They specify things like data transmission speeds and security protocols.
So when I'm choosing a router, I should look for the latest standard for the best performance.
You got it. Technology keeps improving, so newer standards generally offer faster speeds and better reliability.
Okay, I feel like we've gone deep into networks now. We've talked about topologies, wireless networks, and even touched on standards. It's amazing to think how interconnected our world has become, all thanks to networks.
It truly is. Networks have become the backbone of modern society, enabling communication, collaboration, and access to information on a global scale. And it all comes back to software engineering principles, ensuring those networks are reliable, secure, and scalable enough to meet the ever-growing demands of our digital world.
Well, we've certainly covered a lot of ground in this deep dive, from the software development lifecycle to the impact of the internet, e-commerce architectures, and the fascinating world of networks.
It's been a pleasure exploring these concepts with you. And for our listeners who are now feeling inspired to delve even deeper into the world of software engineering, remember that learning is a continuous journey. There are countless resources available online, and even the simplest app on your phone is a testament to the power and creativity of software engineering.
Absolutely. And even if you never write a line of code yourself, understanding these fundamental concepts can give you a newfound appreciation for the technology that shapes our lives. And who knows, maybe you'll even spark an idea for the next groundbreaking app.
I hope so. It's been a fascinating discussion. Thanks for having me.
Thank you for joining us. And for our listeners, be sure to check out the show notes for links to the systems analysis and design textbook and other resources we mentioned today. Until next time, keep exploring, keep learning, and maybe even try building something yourself. CCCI.